Okay, we have Peter Sarnak, who does not need introduction, but he will talk about commutators in SL2 and Markoff.
I will keep this on if you can't hear me. I have a loud voice, but I also have a nasal group. So between the two, I don't want to cough with you.
Some science problems, that's why you haven't seen.
Okay. So everything I say here is joint. By the way, I haven't used this in 2 years, so I probably will collapse on the floor out of energy. I've given millions of Zooms, which is cheating. This is all joined with Amit Ghosh. And not will change it. Meiri. I think I start sending them emails and I get mixed up between you guys all the time. I put in pen and I get both of you. Okay, so everything I say is joint work with them. And I'll explain this let me first explain two problems that I have no idea how to solve. I don't know if they're true or false. The motivation for at least my interest partner in this. So maybe I'll do it. I'll continue away. I think I'm board. So this is a commutator problem, which I'm going to be describing. One commutator. Question. And here, an ancient problem of cubic surfaces. Which are log K3s. What that means, what that word log K3 means, is when you classify surfaces over the complex numbers, these are going to be affine. Always be looking at integer points, like with a Markoff, affine, everything will be affine. And by log K3, when you classify surfaces, you could try classify affine surfaces by taking some compactification of your affine surface and then describing the divisor at infinity. And it's the numerics of that divisor that look like a K3, which gives the name log K3. There's a classification of those. I'll just be giving examples, but these are the most interesting ones Diophantine-wise. In the case of curves, this would be like a curve of genus 0 with 2 points at infinity, an affine curve with 2 points at infinity, which can have infinitely many integer points. And that's all about Pell equation. And in some sense, this is the great generalization of Pell equation. As you'll see in a minute, that's my Markoff. Anyway, it'll be examples. And there's a nice paper of Harpaz, Jonathan Harpaz, from about 10 years ago, where he tries to make where he defines and makes some conjectures about log K3s of the integers. So we're working on the integers, and these are the two problems. So here's Charlotte's problem. Very easy. So question is every Z in SL3Z a one commutator, a commutator. To say if this W will always be this word, one commutator. So if I look at the equation Z equal W of X, Y, you give me Z, and I find X and Y such that Z is in the form of one commutator. I some days think true, some days false. Lubotsky thinks it's false. Shalev thinks it's true. You can think whatever you want. We know nothing. I'll ask a slightly better question in a second, I think. And on this side, so I'm going to give you the hardest log K3 surface. Is every integer not, so here, I'm going to come to the obstructions in a second. We don't know any obstructions, but there could be local obstructions, yeah? Not 4 or 5 or 9. This is an ancient problem. Again, say yes, no, whatever you want. Nobody will prove or disprove you at this point in terms of what we know. A sum of 3 cubes. I find these problems are actually very similar. I will explain. Notice here that 4 or 5 mod 9 are local congruence obstructions. Check. So you work the only obstruct and the only ones. This is elementary. So better to formulate here.
Sum is also different. It's integer, positive or negative.
Not, yeah, integers are allowed to be negative.
Yes.
I'm not aware of that. Exactly. There's a whole literature about sum of 3 positive, but then, of course, there's no local to global principle. And it's exactly you're looking for solutions when one is large negative and the other two.
These are the only. What do you mean by only? Do you have a?
This is the only local congruence obstruction.
What does it mean?
Means that if you look at ZP, you look at the equation over ZP, say P is not 2 or 3. In this case, mod 9. If you look at ZP, P not 3, then there's no obstruction to solving x cubed plus y cubed plus z cubed equals k for any k.
For any k which is not divisible by
No. So I'm just saying that
modulo 9 or modulo any number.
modulo any number. The only obstruction is at the prime 3 and its power. So it's solvable over ZP for every P, and for P equals 3, this is the only obstruction. You have to be clarity. This is all elementary, local stuff. You might have seen Andy Booker some 2 years ago showed that I think 33 was the sum of 3 cubes. That was not known and found it by the smallest solution is 17-digit numbers. And the search way he found it was quite ingenious. Anyway, that's we have some numerics, but there is some integral Brouwer-Manning obstruction connected with that, but it's never produced a failure of this Hasse principle that I'm about to say here. But a better way of formulating this problem here would be as follows. So I'll call it profinite local to global. This will be throughout this talk. This is what I mean. Profinite local to global. Shaleb is basically asking principle for the commutator. So the only equation we'll be looking at theoretically is the commutator. That is, is it true? So this principle is it true that Z equal WXY is solvable. So there's an obvious obstruction. And just like there is an obstruction, if I look modulo Q, if I can't solve it modulo Q, I can't solve it over the integers. So if I look at a finite quotient of SL3Z, and if in that finite quotient, now I'm in a finite group, at least I can look and see if it's solvable or not. So is it true that if Z, the commutator equation, is it true that if Z's WXY in every finite quotient, that's what the profinite means. The commutator. one commutator, is it solvable in SL3Z? Right, so you would have thought that Shalev would have checked this locally, and he has. So continuing, yeah. So we have Tip here, he likes this problem. If you have a finite non-commutative abelian group, simple, then every element is a commutator. That was a conjecture of Corey in that. Corey is my son-in-law. Corey, yeah, you get all the names get mixed up. It's a conjecture of Corey that a number of people were involved in proving. Yeah.
Can you just read these last 3 lines again? Is there like an if missing or something? Just trying to understand what.
All right. So let me say it in words.
Yeah.
I'll say that a local to global principle holds for the commutator in a group. It's an infinite group. If whenever the local to global, the equation is solvable in every finite quotient, okay, then it's solvable in the group. So it's exactly like you would write it here. I mean, there's a whole analogy between solving equations in a group. And that's been the theme of some of this first order theory and so on, is you're looking at what are analogs of Diophantine equations, but in words. But I'm just going to stick to the word commutator, and I'm just going to stick to very simple surfaces. Yeah.
Are you fixing Z, or are you saying that for?
I want it for all Z. Yeah. Now there'll be some Z's for which it's true. I just take X, Y, X inverse, Y inverse equals Z, and I choose that Z. So I'll say there's a local to global principle if that's true for every Z. We can go backwards. And I'm saying that what Shalev, actually quite a few of them, Shalev, Avni, Gelander, Casado proved was that this feature about, so the whole point is if a group's kind of seriously non-abelian, like a simple finite group which is non-abelian, then this map, the map from the product G cross G to G, which takes X, Y to X, Y, X inverse, Y inverse, wants to be onto. It really wants to be onto. In Lie group theory, that's well known for classical simple groups and so on. So the question that they're raising is about an arithmetic group, but if you look at SL3CP, they prove it's true. So the SL3 Yadix satisfies as every element. This is why he's making this conjecture.
What is special? What is special about the commutator? Why?
Nothing. It's just you can't. So if you write down an arbitrary word, everything's undecidable. You're in the world of. It's the same with Diophantine equations. I mean, if you look at all equations, you can't say anything. We're trying to understand. So, I mean, there are other words that you probably can say things about, but I'm sticking to the commutator. And for this talk, it's only the commutator I can say something about because there's going to be a Diophantine. I'll be using a lot of formulae. Okay, so SL3Z has a property that I should give it a name so as to not keep on writing it down. Let me say the words. SL3Z has a property that every Z is a commutator. So every, now of course, the condition on whether Z is a commutator is a conjugacy clause condition. So every conjugacy clause is a one commutator. This they prove would be bigger than or equal to 5. People 3 and 2, it gets kind of messy and they don't quite understand the problem completely. But if you formulate it in this local to global, so if somebody came and found some matrix, some conjugacy clause which locally fails, I wouldn't view you as having solved these real problems. So you're supposed to check. The local stuff's supposed to be easy. That doesn't mean it's easy, but they're supposed to be understood. And certainly in the Markoff case, I'll tell you the answers in more cases. Now, what is special about it? Why did he write it for SL3Z and not for SL2Z? is that all finite quotients in SL, so this is a congruent subgroup property, it has to be part of this course, this seminar. So the whole point is that SL3C, since SL3C satisfies it. Subgroup property, profinite and congruence of the set. This will become important in the case that I'm going to discuss now. Okay, so I would love to say, and these problems seem extremely hard. We don't know how to make points, and we have in this case, which sum of 3 cubes, nobody's ever found a Brouwer-Mannion obstruction. There's reasons for it. I'll say afterwards. If you don't find a Brouwer-Mannion obstruction, then the problem's hard. In fact, you don't even have it. Let me even emphasize this. These problems are so difficult in my view that I don't even have a decision procedure. So this sounds ridiculous in SL3Z. Can you give me, I give you a Z and you tell me whether Z is a commutator. You'd think, I don't know a procedure which after a finite calculation will answer that. Of course, if I give you any Z and he's correct, you will find a commutator. You'll just start looking and say, ah, yes, it is. But suppose you look and look and look and you don't find it's a commutator, at what point do you stop? So I don't even know a decision procedure for that, but I'm going to show you a case we do know about. Okay, so that's the background. That's one way I was drawn into this. Now let me state the theorem that is in this recent paper that we put on the archive, and I'll spend all the time explaining. So we're going to look at SL2, D, instead of SL3, 2 by 2 matrices, friendlier, and D is going to be Z, Z1 over L. Right. And in this case, the congruent subgroup property is not true for the group. But in this case, so in these cases, congruent subgroup property will be very similar. In my view, it's the same problem as Shalev's, it's just you could have asked it here as well. So this holds, this is due to Menaker. It's roughly the same time. They started with bigger groups, Menaker with SL3, then Basel and Sarah, but then Sarah returned to SL2. And the key is there are infinitely many units in this ring. And I'm going to show you how that infinitely many units dramatically changes our whole approach, and is very important for this. All right, so I'm going to ask the same question. Just theorem. The 2 parts of the theorem. The first part that SL2Z satisfies a profinite local to global principle for the congruent, for the commutator, and that will be a whole lecture by Chen next time. So there are many elements in SL2Z which are not, in many conjugacy classes which aren't one commutators, but they are recognized by finite quotients. Let me write it down since finite. This is not. I'll explain it. It's much more complicated than we thought when we started this. Sorry?
Will you have the same for the 3 group?
Yes, okay. Yeah. So that is a theorem of Caleb. It's true in the free group, and this is much more complicated. This is exactly the form. Yeah, so Chen will explain that. This right, so this property, when you say profinite, there's nothing to do with arithmetic. But when you say congruence, and when congruence equals all finite quotients, then you are, of course, landing up in number theory. So, of course, that part one I won't be discussing it.
Okay, regroup in any number of generic.
Yes. And it's a beautiful proof.
Stress that there are other worlds for which it's known that even the free group does not have local diploma.
Yeah, so not
It's the
every
commutator, so it's not
commutator special. They're powers. So I think for powers, Alex Lubotsky proved the local to global for the free group, the same statement. And Thomson showed it was false for, there was, so for congruence, it's going to be similar to what I have here. So he showed it was, no, so I think he showed the same. It's true also for SL2Z, but through all quotients. Yeah. The powers happen to be quite a bit easier than the commutator. Alex told me.
Is the statement about powers true in SL3Z? The result about powers that you just mentioned.
No, he's also got powers in SL3Z. I think, I don't know.
Certain, just a second. No, I believe it's false. Actually, I will check it out. What question? I'm supposed to know to answer the question.
Okay, so what I'm going to talk about today is the second part of this theorem. For SL2D equals Z. This is not hard because it's very close to a free group, but I'm going to give a treatment which is arithmetic. So for D equals Z or Z 1 over L. Things quite subtle. We have to assume L is plus or minus 1 mod 5. I have to make it complicated, but anyway, the main point is we want to show that it fails, so it's enough to give the congruence. Local to global. So by congruence, I just mean you test your equation in all congruence quotients. Congruence local to global. Fails for infinitely many Z, many conjugacy classes Z. So I'm going to give you examples of this. And in particular, it's a congruent subgroup property. It's true, particular D equals Z 1 over L. That ring, we have profinite fails. Commutator, because the profinite is the congruence. Okay. So I want to explain the second thing, and the second is where we will connect it to a Diophantine equation. Now, of course, even Shalev's question is a Diophantine equation. You could write down x inverse y inverse equals z. Z is given. You're trying to solve for x and y, 3 by 3 integer matrices of determinant 1. You write down all the equations. It's an algebraic equation. It's an affine variety. And you're asking, is it true because the congruent subgroup property is true? Now you're asking, is there a local to global principle for this strange equation? Now, if it's coming from a group, you'd expect to use the group rather than number theory. But of course, the whole point of this seminar is the mixture of the two, where you go back and forth, and we saw Jim Ren speak about the use of Lang's GM to show that you don't have bounded generation where you use a serious number theory. This is in the opposite direction. I've always been interested in problems where you try to produce solutions when you might have solutions, and that is really difficult. We really don't have ways of making solutions to integer or rational, except very few sparse things, unless you have many variables and what's called the Hardy-Littlewood circle method works. Other than that, we live on what we can do. And we have to specialize. And so now I'm going to look at the equation which has been discussed in one way or another. And so I'm going to discuss part 2, and I'm going to divert these Markoff-like surfaces. What I say is true for slightly more general ones, but I'm going to look at this. So I will relate, of course, the problem, this part 2 that we saw to this equation, and I'll show you this is the beef, so to speak. Markoff surface is x1 squared plus x2 squared. That's x3 squared minus x1, x2, x3. And by mk, I'll mean this equals k, and in free space. So that's this variety, and k equals 2. I would always assume k is not 2 because k equals 2 is special. That's the Cayley cubic, and everything I say is false for that. That's trivial, so to speak. It's the reason Cayley singled out that cubic because he was able to compute everything on that cubic and then use this to prove 27 lines of cubic.
K equals 4 especially. This in your formulation.
You're right. I'm already jumping to the application, which is when k it's k minus 2. You are absolutely correct.
It was MK then.
What? Oh. You got me. All right. So I'm going to discuss the case D equals C, and then I'll extend to these rings 1 over L.
Sorry, what's the difference between Markoff surface and Markoff-like surface?
It's singular. When I get to things, you will see the difference, but the surface is singular. In fact, the Cayley cubic has the property that it's got singularities, if you call, which are cone-like singularities exactly at 4 points, and it classifies the Cayley cubic. So it's non-singular. These other ones are non-singular. They're log K3s, and I want to discuss the divergent geometry.
So what does log K3 mean in this case?
It means there's a compactification in which the divisor plus the canonical divisor, the complement at infinity, the divisor infinity plus the canonical divisor is linearly equivalent to 0. That's what I mean. So it's exactly the setting in which Voita would not say that the two can't be a risky dense set of points, because that would be the sum of one side. Then there are very few points, and if the sums of the other side, then there are many points, and well, you can't prove it unless you make more variables. This is always a threshold. This is the most interesting. So in the case D equals Z, Ghosh and I, so we've seen Chen speaking about the action of the mapping class group on the case K equals 0, the Markoff surface. That is important in all these cases. But what Ghosh and I set out to do, so let me call this M of X, this polynomial in 3 variables, is we have developed a few years ago. We have studied this Hasse Principle. I want to show you what we found because we'll be using it. Exactly for the same as sum of 3 cubes or this other problem. We found something rather interesting. So the first thing is very easy, the analog of congruence obstructions, so that we know what we're talking about. So. Then I'll explain why we can deal with Markoff and not with sum of three cubes. And you all know why. The whole point is a character variety, and we have this descent on it. Okay, so K is admissible. I'll call it admissible. If there are no local combinations. So I'm working over Z. I'll also assume K is not a sum of two squares. You can deal with a lot of it in that case, but of course, if K is a sum of two squares, you set one of the variables equal to 0. That's kind of a trivial reason that you have a point on the surface. So I'll assume K not a sum of two squares, which of course, and then call it generic now. So K is admissible if and only if K is not 3 mod 4. So there's only obstructions at prime 2. K is not 3 or 6. By the way, in any of these cases, it's obvious that you're only going to have finitely many progressions that you have to deal with. It's not tricky, this. And that's because if I'm solving this modulo P, and P is large, then there will always be solutions just by curve, by elementary methods or Riemann hypothesis for curves, Lang way or anything like that. So once P is large, it's okay, and then things stabilize when you go over prime power. So studying that over ZP is not difficult. So these are the admissible Ks. And the question is, for which Ks do you have a solution, and for which Ks do you not have a solution? So they have to be admissible, and once they're admissible, you can try to find a solution. Now, very different to the sum of three cubes, we have a descent algorithm. This was explained last time by Junho Wang, that for any of these character varieties, so this is the character variety of the one function torus, that's a connection to. I won't go there. Of course, you can find the action of the mapping class group directly, the relative character variety of the one function torus, which seen many different views on, and it's in fact the fact that there's so many different views that makes it so interesting, including the, say, the talk of Will Chen in terms of G structures of elliptic curves. So this is a character variety of the one function torus, and very generally the character variety, the relative character variety. Relative means that we fix the trace around the loop around the hole to have trace K, that's all that. And so the mapping class group of that one function torus acts on the character variety. The variety is defined over Z, and the most important thing is this mapping class group always acts taking integers to integers. This is what's going to allow us to do things. I'll call this group gamma. Acts on MK, and gamma takes MKZ to MKZ. So this has two big advantages. If I have a point, I will probably have many points, but I don't know whether I have a point. That's always the issue. It's like on an elliptic curve. You first got to find a point, and then you can start to add. So if I have a point, I'll probably have many points. Will I have infinitely many points? That's a subtle issue, and that's an issue which I'm hoping that we will talk about later in the character variety seminar, which is connected with Paine-Lavey, finite orbits of the action of the mapping class group on 3 space And there's a beautiful classification in studying Taylor base 6. We understand what the finite orbits are. So it could be that I'm on one of these surfaces. I have a point, but I only get finitely many out of it. That's very rare, and we understand. So the moral of the story is once you have one point, you're going to have a lot of points with these Zariski dense and these transitivity properties that Chen was talking about will give us essentially something like strong approximation. So once there's one point, this thing makes it very rich. That's something you don't know about sum of 3 cubes. So we know 33 is the sum of 3 cubes, but we know one solution to that. There should be a Zariski dense set of points. Probably. As I said, you can say whatever you like in that case, and I can't prove it. So in this case, this is the big help, at least if I have one point. But what Ghosh and I study is when do we have a point? So when is the Hasse principle true? And the other thing you can use this for is descent, which was already done by Markoff, and which Juno was explaining. We have this descent for any character varieties in absolute generality of character varieties of a surface group into SL2, at least that's what he's looked at so far.
So descent, you mean the big solution can be.
You can bring it out, but then the question is, can you bring it into a compact set? And that's what Wang explains. You can use differential geometry to actually, that's who has this remarkable thing using Loevner and Gromov in terms of these systems. That secretly was what is allowing him to bring him into a set so that he could decide if you have a solution. So, of course, if you have a solution way out there, which we've never seen, if you can bring it down to where I can actually inspect, then I can do it. Now, when we started this, we didn't know which case would be, which wouldn't. And I urge you to look at our paper because Amit Ghosh found a fundamental domain for this nonlinear action, which is much prettier than Gauss's fundamental domain for the action of SL to Z on the upper half plane. I call it a Ghosh fundamental domain. It's better than a Gauss fundamental domain. And once he found this fundamental domain, it's given by a cubic equation, and the set is given by hyperplanes very similar to Gauss. Then he could run very quickly, and he went up to 10 to the 9 instantly and computed which have Hasse and which don't have Hasse. And here's the answer, and that's kind of surprising and a warning in all these problems. But the minute you have structure, the story that if you want to be in a club, you can only be in the, if you want to be in a generic club, it's very hard because the only thing you can always do is have some special feature and then you're not allowed in the club. So of course this has got some structure, and the minute you remove the structure, like with sum of 3 cubes, then somehow randomness may say that it's true that every number is a sum of 3 cubes unless yeah, there is an obstruction. So there's a fundamental domain. I don't want to write it down. Paper. Which allows check and to make tables of how many, definitely many orbits. So these are like the class numbers. Actually, if you read Gauss's Disquestiones Arithmetica, the very first thing he did after he defined class number is he computes the average of class numbers and he looks at statistics. He always liked to look at the, Lax once told me that if Gauss lived today, he would be tied to his computer and be just hacking away at data. He loved data and so if you read Disquestiones Arithmetica, he defines a class number, he's got this reduction theory, binary forms. Then he computes them for many Ds and then computes the average. And of course, the reason you can compute the average is that you're counting something in a volume, as he knows. And so you can do that here. We will be doing that. So the fundamental domain allows for checking. So I know what it is. For little k less than or equal to capital K about 10 to the 9. And the remarkable finding is that there are many Hasse failures. About, and it looks to have settled very seriously, because we can't prove anything like this. There are k to the 0.88 roughly that's a fact. That gives you your marching orders as to what you might want to prove first. And I want to say a word about what we prove. That's just data. So there are many cases for which there are no solutions. Not because of congruence. Right? The fact that you can decide it is because of the set. All right. So that suggests very strongly that's one of our main theorems. That for almost all k, the Hasse principle is true. In the sense, not in the sense of how many k's up to k's are true divided by k, or how many admissible k's fail Hasse, little o of k. We only get little o. This is a tricky theorem. So that's of course suggested by that. That's k to a power less than 1. But so almost all. I'll say a word about the proof of this because we got stuck on a point and I don't want to make this mistake. And if anybody is working on this, don't set yourself back. Amit and I set ourselves back for maybe 6 months. So if you want to prove something like this, you want to count the number of points in some region. So you're really looking at the map, this M of X, and you're trying to see what does it do to a box, say, with side lengths T, and then what values does it assume? You're trying to see that you hit many values, almost all values. If you try and do that, and you just take positive integers, you've looked at the wrong column. You should be taking regions which are near the 0 set, where you might have an excess, so that, and the numerics indicate, by the way, that there'll be solutions which are large, for which M is smaller than you expect, so that at least if you looked at those class numbers that I was saying, you compute, those class numbers grow slowly on average. So that indicates that you should be able to do something like what I'm about to say you do. There's just one point I want to make is you look in a region where there are more points than you might expect. So you take growing regions, something like you were talking about, but not balls. So omega suitable growing regions in integers, so we're looking at R of 3. So they're compact regions, they've got a parameter, maybe k. And you look at R omega of k, which is the number of x in nkz. No, of course, intersect. So the number of guys on the level set intersect omega k. And the average of R omega k you can compute, and you want to show that R of k is not 0 when k is admissible. It tries to be not 0. And the way you're going to get an almost all result is almost some kind of variance computation, but the variance is not the variance. That's all I want to point out here. Consider the following expression: the sum k less than equal to k of R omega of k minus something squared. That's what you're going to hope to show is small. But this was a mistake. We were putting the mean value of this there. Very stupid. Couldn't get the variance to go to 0. What you put there is what is dictated by the local densities of the number of solutions, product over all primes times the Archimedean solutions. So there's something called the Ziegel mass formula, which is also the leading term in the Hardy-Littlewood It's a product of local masses. I think you wrote an undergraduate thesis on this. Interpreting the adelic. Somebody told me that. Is it true? Okay, great. So there's a product of local masses, which is what you should expect the answer to be. It picks up that if at some prime p, there are no solutions, it'll put 0 there. So it'll immediately pick up the fact that something is not admissible. And of course, it's a number there, which of course is not the number of solutions, and it could be 0. It's just a product of local masses. This is not in a region where anything looks like it's reasonable. It's the way Birch and Swin and Dyer also found their conjecture by running these kind of things. So anyway, I think the most important thing here, which of course everybody does, but I'm just saying we were stupid for a while, is the expected number of this, which you can write down, expected number in terms of solutions. In terms of local densities, p-adic and Archimedean squared. And then this involves that thing squared, this thing squared, a cross term, all of which are extremely difficult to handle, but that's the main achievement of the paper. I'm not going to explain that all. And we show that that goes to 0 and eventually get almost all Hesse's true. And the fact that we can do that here is primarily because of, not to do with the action, not because of this descent argument, but because of the nature of the cubic. I should just say that. So at some point you'll have 6 variables because you're squaring. So you'll have m of x equals m of y. That's that. If you write a sum of 3 cubes equals a sum of 3 cubes, nobody knows how to count the number of solutions. Victor Wang, in his recent thesis, just finishing this year, showed how if you assume all sorts of conjectures, you can actually do what we're doing here. But here we deal with it unconditionally, and there's something, again, that we use by the fact, I'm just pointing out what's important about the Markoff inhomogeneous form of this, is that we have 6 variables, but if we fix 2 of the variables to be small, then the equation in the other variables is a quadratic form in 4 variables. And quadratic forms in 4 variables, this is what we know how to handle quite well. And that all that machinery comes in. So it's the feature that there's a natural way of choosing 2 variables to be small and still do the right count. The other hand, when you have a sum of 3 cubes, it's not clear which variable you want to make. And they're all sort of there's no obvious way unless if you fix one of the variables, you get to cubics, about which we know much less. All right, so are there Hasse failures? Yes, there are from the descent argument. But can we produce Hasse failures by using some better argument so as to prove the infinitely many Hasse failures? And that we did. So, and that's going to be the source of the fact that the commutator problem also has a facet, has a failure. I'll explain that. I'll explain it in a new way. It's very clean. This has evolved through iterations of other people. I'll explain that. So our first proof was just bare hands. So there are, these will be the basis of these part 2 of this theorem. They are k to the half, k to the half, Hasse failures. Coming from. So there's one tool that mankind knows to try to find Hasse failures, that is failures of local to global principle for various kind of equations, which are, so remember we're only looking locally, but maybe there's some global thing that tells you that locally something is not prescribable, and that global thing is reciprocity. Come from some kind of reciprocity. In this case, quadratic reciprocity might be cubic reciprocity or any class field reciprocity. So we found a way of building in reciprocity. I'm going to explain it now to show that they're at least k to the half Hasse failures for Markoff. Once we did this, I should say that Commutator has done something very interesting for people like me who work over integers. There's something called the Brouwer-Manin obstruction, which you'll see its flavor in the presentation I give right now, which is about rational points on varieties, Brouwer groups, and a reciprocity, a global reciprocity used to show that there can't be rational points on certain varieties. Commutator has defined an integral Brouwer-Manin obstruction. He's defined an integral variant of it. And once he saw what we did, he explained most of what we did here as an integral Brouwer-Manin obstruction. But I'll give it a presentation where you'll see that it's our lowbrow thing and it's clearly related. It's clear why he explained all of them and no more. We found them all. So this was done by Commutator. So we found this directly. I'll show you some variant on it. But then there's some interesting papers of Commutator following that. Jointly with Chen and Shu, and separately by Laughlin. Yeah, I explained in terms of the Brouwer group of these affine surfaces, which, as I said, are smooth. So they compute the Brouwer group, and then they actually explain every one of the examples is a Brouwer-Manin obstruction, integral Brouwer-Manin obstruction in their language. All right, let me explain it. It's quite easy. I think that this comes, you'll see what we had, but this version will be, I think, very clear.
Sorry, Brouwer-Manin.
I'm about to explain what is essentially Brouwer-Manin. What?
The commodification.
What?
Do we need the commodification?
So, no. So they'll compute the Brouwer-Manin for this affine surface. Smooth. They need it to be smooth. All right. So for X in MKZ, so I'm going to take a ternary quadratic form, and I'm going to use the Hasse invariant for that ternary quadratic form and some form of quadratic reciprocity to write down a condition. So if I take X in MKZ, let's look at the following matrix: 2, 2, 2, X1, X2, X3, X1, X2, X3. That's a quadratic form in 3 variables integral. If you compute the determinant of this, the determinant, so sorry, all right, let me let this be this quadratic form. Let me take 1/2 of this. So f of x will be the ternary quadratic form integral corresponding to this. I divide by 2. U1 squared plus 2 squared plus U3 squared plus x1 U1 U2 plus x2 U2 U3 plus x3 U1 U3. I'll mix those up. So this is a ternary quadratic form. I've divided that by 2 over there. If you compute the determinant of this matrix, you'll see it's the Markoff. That's a cute computation. That's Markoff, the Markoff form. That's what we'll be using. So if you look at the following, the determinant, I think he said I can go here, right? The determinant of A, this will be relevant, is minus 2 into k minus 4 for x in MKZ. So this is just about this matrix, and then of course that's just one half of that.
I lost you, Peter. I don't understand. This, what is the connection between this f, x?
This is a symmetric matrix.
Yeah.
But defines. So I'm just. This is one half of that. I'm dividing.
This is one half of that. This is in the U1, U2, U3.
I'm just writing down what U transpose this U would be and dividing by 2. So it's a ternary quadratic form. So for each solution to the Markoff equation with the value k, I have a ternary quadratic form. Now, locally at each prime p, if I have a quadratic form, I have the generalization of the signature. So when you're working periodically and you want to know whether 2 quadratic forms are equivalent locally, then they must have the same, over the reals, they must have the same signature. Over p-adics, they must have the same number of variables, of course, and the same discriminant, determinant, and they must have the same Hasse invariant. The Hasse invariant is like the signature p-adic.
What is A now? Did you auto?
A was this matrix. This is what I'm saying. I was just saying that the reason this is going to work is that the determinant of this matrix is the Markoff equation in X. That's.
But there's no K in this matrix.
No. So the determinant of this is M of X.
Yeah.
And if X is in MK, then M equals K. So the determinant is given only by you don't need to know X1, it's given by K. All right. So now let CPF be finite and Archimedean be the Hasse invariant given by the Hilbert norm symbol. So it's, if it's diagonal, it will be the product of all the Hilbert symbols of all possible A1s to ANs, different ones. So the Hasse, let CPF be the Hasse invariant, which is what's used in classifying quadratic forms of the p-adic. So let CPF be the Hasse invariant of F. It's plus or minus 1 value function locally, and the product of all p, including infinity of CPF, is 1. And that follows from reciprocity, quadratic. That's equivalent to quadratic reciprocity. So if you have an integral or a rational quadratic form and you write down its Hasse invariance and you multiply them together, you get 1. And this, of course, is what Hasse was answering. If I give you a quadratic form and I want to, suppose I give you an integral rational quadratic form and I want to know, can I realize the thing locally at all places? Well, you have to have the Hasse invariance right, that the product of these locals have to be 1. That's the extra condition which allows you to say the only obstruction is this product is 1. And the Brouwer-Manning groups are defined through exactly generalizations of this to algebras rather than just quadratic forms. So this is clearly of that nature. And what's that going to do with our problem? Well, it's not difficult to compute because this determinant is k minus 4, and this is 3 variables that you can compute for our equation. And we found this directly by changing variable and making elementary computation. But this is now explained, I think, a little bit more clearly. That, so compute that CPFX for our f of x is defined there, where x is a solution of that. Doesn't matter, it could be any one of these 3 variables, x1 squared minus 4, k minus 4. The Hilbert symbol, which is whether the this times x t squared plus this times v squared might equal -1 as a p-adic solution. So you can actually compute very easily the Hasse invariant, And what we learn is that the product of these numbers, these CPFs, if there is a global solution, must be 1. So it may be, and now this is a very delicate business, and this is why Commutator has never been able to his frustration, show that there is an obstruction to a sum of 3 cubes. What you can do is you can easily see this will immediately, any invariant like this will say that certain congruence classes, idyllic points, will not be realized by a global solution because there's this product has to be 1. You have to be trivial in this group when that's the same in this Brauer-Money. But how do you engineer it that some very strong form of strong approximation must fail? But to have a Hasse failure, you have to actually say that there's no congruence condition put on there. It's just there's no solution. And so you have to actually go and find some situation where you can find specific numbers where no matter how you choose X, because you don't have any control on X, that X will be whatever it can be. And you still want to be able to say that this product can't be 1. And if it can't be 1, then there can't be a global solution. And that's exactly what we do. So we found it, and we found all of them, and they found the same set algebraically. And so here's an example, and I'm going to make this is the basis of the example. I'm running this. Only that's Blackboard, which is good. I'll give you at least one example here. Check it. So using this, and the product must be 1. If K is 4, this was the first one of the main ones we found. You having all of its prime factors. This is just to negate, no matter what x1 is, the fact that their product, when all its prime factors plus or minus 1 mod 8. K is generic. K is generic, which is issue really, and admissible, which it's a different set of congruences, and admissible. Then K is a Hasse failure. So we found this condition directly, I think, which is multiplying them with after a lot of changes to those. And K is a Hasse failure, or MK. This is infinitely many Hasse failures, which is infinitely many numbers like this. They're roughly square root of capital K of them up to K. And then we made more. That's not the only one. We found finitely many like this. And then we were able to combine that with descent and make a new slew of counterexamples, which make use of descent and Brauer-Money obstruction, so that not all we can construct infinitely many examples which are not explained just by Brauer-Money. So if you thought that the statement, like some people like to believe in some situations, is that the Hasse principle is true except for the Brauer-Money obstruction, this is false, yeah? We saw it numerically, handsomely false, but we can only make, using this kind of argument, K to the half, while they're really K to the 0.8. And so you should just keep that in mind in these kind of problems where you have very sparse set of solutions, these log K3s. This is one of the few that, the only one that I know that we understand something about at this point. All right, so that's how we did it here. And since I'm running out of time, you can imagine I can do this over Z1 over L. But I can't do the descent over Z1 over L. Let me just explain that. So something changes dramatically when you change mapping class group when with respect to Z, it just fits right, finitely many orbits. If I look at the ring Z1 over L, the mapping class group acts with infinitely many orbits. And that's connected with the units. The units are what made the strong the congruent subgroup property true. The units are also stopping me from acting with a mapping class group with finitely many orbits. So at this point, I don't know, or we don't know, even how to decide the problem over ZL, as we do know, because of descent over the integers. We are working on this. We're close to understanding this, I think. The group is still very big, but this is the beauty. There's a change on both sides when you change from Z to Z1 over L. If you're lucky enough to find a Hasse failure, you might algebraically still push it through, and we will do this. That's going to be our solution here. But the fact that Hasse failure is sort of common there just because there are no points and we don't know how to show it might be a much more robust way. Anyway, over Z, that's what's happening. When you go, I repeat, from Z to Z1 over L, the congruent subgroup property kicks in. The profinite becomes congruence. And at the other side here, we lose control, one important piece of control, and that is that the mapping class group is no longer acting with finitely many orbits. All right, so I saved some time by saying that in words. Now let me explain the relation between this problem and the other problem. And there are three varieties here. They're all interesting, and the most difficult one is the Markoff. So in this problem of the global principle for the commutator, the Chalet problem for SL2 of D, we have the following. So you have three equations. I want to say a few words about that. So the first one I'll call CZ, C, and it's WX, Y, the commutator word Z, and Z is in gamma D. So and I'll call this T. That's going to be the trace of the word. We are 2 by 2 matrices. I can compute the trace. This will be this is an equation for x and y, and it only depends on the conjugacy class of z, and you can divide by simultaneous conjugation, as we always do in these character varieties. The trace, of course, preserves that. So this is we solve for x and y. Always you're solving for x and y here in SL2D. Yeah. Here we fix z and we ask, is there a solution? And we're going to be assuming there's a solution in every congruence quotient. Is there a solution, global solution? Then we have m plus 2. That's why I got mixed up at the beginning, which is our Markoff equation, as you know, m of x. Right, so these are three affine varieties. And there's a morphism from here to here and from here to here. There's a map behind preserving integers. So the map from here to here, I think I'll call it I side. So the map from here to here, if I have Z is the commutator, then I just take the trace of this, and then T is the trace of Z. So if I have a solution upstairs, I get a solution to that equation. That's trivial, but the inverse map is not, that's a subtle thing, the lifting thing. And that's one thing I want to point out to understand completely in terms of at least decision procedures. And then we have this map. This map is a fantastic map. This is the map that Fricke discovered. So if you have, let me just say this map, psi, you have x and y, two matrices, 2 by 2 matrices of any ring. Then if you take the trace of x equals x, it's one trace of 2 trace xy is 3. And you can verify in 2x2 matrices, you use Cayley Hamilton, that's an easy exercise. Then x squared, so m of x is t plus 2. So if I have a solution here, then I get a solution here. If I have a solution here with the parameters as such. Now, are these equivalent? No, but in terms of decisions, they are easy. So if you understand this, this is the most important comment I want to make about Markoff here in this problem. If you understand this, you understand the other two decision-wise. And that's because the lifting problem is a problem of the type of looking for points on a variety G over H, where G is SL2 acting on some ring of coordinates. And that's exactly what Borel and Harishchandra solved in the linear case, that if you have a variety of the form G over H and you look at the integral points, then the group acts on the integral points with finitely many orbits on the affine variety. And as I think Chen mentioned, Siegel and Grunewald showed that everything's effective here. So you can turn that reduction theory into a decision procedure. And so you can decide the lifting problem here without too much trouble from the linear theory. So this is all a nonlinear theory. This is the big. So in terms of if I want to decide, like in Shaleb's problem or this problem, in this, when we're looking at SL2 of D, any of these rings, if you understand Markoff, you can understand that for each given Z at least. And then you would probably be able to answer most of the questions. Yeah?
So are you saying that already as a black box, like
as a black box?
from the fact that you know that us failed in the one,
I'm going to use that. Yeah, right. So I'm going to build that, but then I have to make sure that the local congruence obstructions, they become different in each problem. So I will give you the answer right now. I'm going to write down the exact matrices, don't worry. You'll see them explicitly in a second, then you can verify that they are counterexamples up top. So obviously, if I have a counterexample at the bottom, it looks very likely I could lift it to the top. Since most of them didn't lift, but we found some that did. Because some of them lifted up and then had a failure at the top. had an obstruction that you saw locally at the top, which shows that there may be other ways of seeing things.
For the local.
Yeah, I'm going to write down that the local to global profinite Hasse principle for commutator fails for SL2D, where D is 1. D is Z1 over L. I'll write the counterexample.
I'm just curious.
Coming from those.
I'm just curious. Can you really just?
I'm not saying they're the only failures.
No, I understand. But can you deduce it just on the fact that the Markov failed without understanding even like this is?
No, right. No, right. The counterexample you can do almost with. Yeah, it's done in the paper. What I'm saying to you, however, is if you wanted. I mean, before you start asking hard questions like, is a number sum of 3 cubes? I might say, can you even decide whether a number is the sum of 3 cubes? All I'm saying is the decision procedure would be for the first problem, which is our commutator problem, would follow if I knew a decision procedure for Markoff. And we discuss that in the paper in detail. So Markoff is...
Before you erase, can I ask this A sub x? A sub x, do you have an analog of this for other character varieties? Because it has geometric.
There are Procesi has some very interesting varieties, higher dimensions, and we hoping to tackle SL3. We still going there. The answer is yes, there are many of these, and there are actions of this type. Just 2x2 matrices where everybody starts. That's where some of us end. Okay, so the answer to you, Alex, is this part doesn't require any decision procedure. This is a matter of if you have a counterexample for Markoff, it looks very likely you'll have a counterexample.
So
everything.
So that's what I don't understand. The likely just be,
no, you have to check that your counter.
The local.
Only the local issues are just right. Correct. Right. Let me write down the counter. Now, I want to make this very important because to me, the Markoff is entering in so many different ways now. It comes in your simple closed geodesics on the one Commutators, in his G structures, in Markoff, of course, in terms of diaphragm approximation of rationals, the word, Markov spectrum. So there must be some reason that it's so fundamental, and we want to discuss still Taylor basics, another interest in Markov. Yeah, so this character variety seems to be very rich and special. Okay, let me just write down that one example because I'm writing. Yeah, okay. Let me end with this, so I don't want to keep it. And what I'm going to then, in the next term, the character variety part, or however we continue it, Alex Gambit or myself will give a lecture that complements Will Chen's lecture about the action of a mapping class group over the ZP points and the fact that it's acting minimally, which is the main achievement there. Thanks, he's completed that, at least for Markov, for the Markov numbers themselves. Okay, here's a theorem for L. Congruent to plus minus 1 mod 5, that's our prime. We weren't able to, we haven't found it in other L's. So these are not automatic. You can always have, I repeat, you can always arrange a failure of strong approximation in some form, but to actually have a Hasse failure, you need much more miracles so that you've kind of covered all the classes. E equals Z1 over L. So we are promoting that example to this. P equals 2 plus 20 nu squared. Nu and only this one worked. So these are independent congruences, so there's no problem there. And the most important thing is, because you want. So Alex, you might think of how you have a group theoretic understanding of what I'm about to write down. This is coming from quadratic reciprocity. That's the moral of the story. It's coming from multiplicative properties, plus or minus 1. Okay, so infinitely many such T's, and now you take the following matrix, conjugacy class, Z, T minus 5, right? So it's got trace T. The congruence will make this integers. 5 nu minus 2. Determinant 1 you can check. Plus 2. This is in SL2 Z1 of L. I'm going to type in SL2Z, but I'm looking at it as a conjugacy class in this group. Satisfies, so you have to go and check this, it's quite painful. Satisfies satisfies is a commutator in every finite question, is a commutator in but it's not a commutator. That's the answer to Shalev in this example. And there are infinitely many such. Yeah. So it's not that it just lifts, you actually have to make sure that all side conditions, and that takes some calculation. That's all we've achieved definitively at this point. And so whether Shalev is right or wrong, whether every number is a sum of 3 cubes, well, we won't probably know for a while. At least I won't. And as I say, I'm going to either me or Alex Gambit will give a lecture on combining what Will has now proved to show something that I think is quite beautiful, and that is that the mapping class group acting on the integral, p-adic integral points. So if you look at any character variety, this is just for the Markoff type, XZP, that's a compact set, and it acts minimally. Basically every orbit spins. That's much better than ergodic in connection with what we were talking about. Maybe Shah has proved something like that. I have nothing against discrete action, but this as a compact space, a big group acting on a compact space, acting non-linearly, and it acts with one orbit. I think that's a fundamental. Yeah. I'll stop.
Some more questions?
I had a question or a comment on the first part of the talk.
Yes, go ahead.
For the just I don't know how relevant this is, but when the fact that the commutator map wants to be onto,
Yeah.
that's pretty far from being true for some real semi-simple groups, such as the universal cover of SL2R. There, the image is has interior, but it's rather small, and that's basically the root of the Milner-Wood inequality for the Euler class for surface group representations in PSL2R.
When your center is so cold.
Yeah, so, yeah, right. You really don't have anything commuting trivially because you don't get much mileage from X inverse, Y inverse when you commute, right? You don't produce new elements. By the way, the proofs by Tip and Shalev in the finite, the whole point is that when you're finite, you somehow know where to go, and if there's no structure, it's kind of a combinatorial theorem. In fact, they prove it using bounds for characters, right? Character sums and the formula for Frobenius. So I would say in the infinite group case, yeah, if you're compactly grouped, like then these things are standard theorems. So yeah, but for SL3Z, you have any feel? Yeah, well, that's when I heard this question, I thought Alex tried to disprove it that most aren't commutators. He was hoping that if you do a random walk, you would never come back to where you started. But that, I think it's probably almost true. I think it's trying to be true.
What about
the lesson changed, by the way? Not this. What? Sorry.
What about the extension of order 2? Like when you lift SL3Z to the double cover of SL3R?
I don't know. You can ask this in every area. Maybe Tip. So what's the? I guess you just have a finite group viewpoint. There's an even stronger conjecture, right? This.
Well, I mean, like over there, you.
Thomson conjecture. What is that? That any conjugacy class?
No, there is a class where the square is the entire group.
There's a conjugacy class who squares the whole group. S times S is everything. That's open.
Well, I mean, like it's open, but only for the simple group over some finite field, and we Michael and I we proved that some indeed.
So I think the moral of the story is that in finite, if you have a finite simple group, so if the quotients are very close to being finite simple groups, then the local obstruction's not there. And then the question globally is, at least in this example, got every flavor of a kind of surface that we study. It's, as you can see, I'm saying that the Markoff is really, so the minute we understand Markoff of an arbitrary ring, we'll understand this problem, but we got a ways to go.
Yeah,
so we have a lot of understanding of some aspects for that. Yeah.
I mean, in the finite case, then you can also count the number of the representation that you can write as a commutator, and we expect some.
Right. So in the finite case, you're proving it by counting.
Yeah.
Yeah, it's extremely hard to prove anything by counting because these things are so sparse. Counting is this hardy Littlewood circle method. If there's tremendous number of solutions which you have, then you can hopefully use statistics. This is why I'm so taken by this. So before this, my favorite theorem was which numbers are sum of 3 squares. Gauss's favorite theorem too. By the way. When he proved this in his Disquisitiones, he writes Eureka. And he thinks this is the best thing there. And he knew which numbers are sum of 3 squares. It was natural at some point to say which number is sum of 3. It's a kind of problem like that. All right.
Thank you very much.
Yep.